Um, Hello, everyone. So my name is Jiakang, and I'm currently computer science PhD student at Rutgers University and supervised by Professor Eddy. So here, I'm very honored to be here to present our work, Genesis. So this work is a collaboration between the Rutgers University and North Carolina State University, supervised by Eddy Zhang and Professor Huiyang, Professor Yuan. So let's look at the nature world around us. So if we can simulate the nature, then we can harness the nature. So, but it was recognized that the classical computer struggled to manage the vast state space of the quantum mechanics. So back in 1981, Feynman first suggested to simulate the nature through the quantum computer, since it can naturally replicate these systems using the quantum entanglement and quantum superposition. So while the nature, in a sense, is made of all kinds of physical processes like the early universe, the black hole, or even microprocesses like the particle collision or molecular chemistry, right? So an ideal quantum computer can simulate efficiently any physical system that occurs in nature, coded by John Prescott, a very famous professor in Caltech. And during the physical processes in nature, all physical systems, including atoms, molecules, and materials, obey the law of the quantum mechanics. And the complete information about such a system is encoded in its Hamiltonian H, which governs how the quantum state evolves over time via Schrödinger's equation. And the process of simulating the Hamiltonian is called Hamiltonian simulation. And if we can simulate the Hamiltonian exactly, we can predict the future behavior of any quantum system, like its dynamics, its like energy level, and response to interactions. And that's leading to many applications like in drug discovery, molecular biology, and quantum chemistry. So most current like quantum machines use qubits that are discrete variables, DV systems, and for fermions whose degree of freedom occupy discrete states are very friendly for DV systems. And in contrast, the CV system, the continuous variable quantum system, Q mode, has a spectrum of many possible states, like theoretically an infinite continuum of states. And in this case, bosons, whose degree of freedom occupy continuous states, is very friendly for CV systems. However, there are some, shortcomings of both CV and DV owning systems. So for CV hardware, it can benefit from the infinite dimensional Hilbert space, but it is challenging to have known Gaussian resources. And DV-only hardware needs truncation for simulating the continuous variable states, and it is very difficult to simulate the native bosonic operators. However, hybrid CV-DV hardware takes the best of both systems and is well suited for the physical simulation of fermion bosonic mixtures. So currently, several quantum architectures are supporting the hybrid CV-DV systems, including the superconducting and trapped ion and neutral atom. So for superconducting quantum computers, we can see that the DV systems are corresponding to the qubits, highlighted in purple, and the CV systems are corresponding to the Q modes, highlighted in the green rectangle. And each Q mode is connected to a specific qubit, and only the Q modes connected with each other in a lattice-like coupling graph. So in this work, in Genesis, we will primarily focus on the superconducting architectures, and it is also applicable for trapped ion. And we do not consider the neutral atom architecture, as it does not allow the connectivity among qubits. So as mentioned previously, the hybrid CV-DV hardware takes the best of both systems and is well suited for this physical simulation with the fermion boson mixtures. Among previous works, tools like bosonic Qiskit, strawberry field, Perceval, and Boshedro, although they offers compilation support for CV-only systems, but is not applicable for simulating the mixtures. And also, domain experts may need to manipulate the unitaries for benchmarking and programming using tools like Qtip. However, compiler for the hybrid CV-DV systems remain largely unexplored. And Hamiltonian simulation with fermion boson mixtures interactions have not been thoroughly investigated. So the Genesis actually just tries to bridge this gap to offer a complete end-to-end Hamiltonian simulation compilation support. And at this point, we can summarize several challenges and motivation for our work, which are Hamiltonian simulation compilation is actually a complex interdisciplinary problem as it actually involves like many physical backgrounds. So we have actually like investigated for hundreds of physical papers for the compilers to obey, and also in its knowledge for the compilation and optimization knowledge. And so we offer domain-specific language, DSL, Hamiltonian grammar representation to better represent the Hamiltonian in a compiler-friendly way format. And multi-level compilation to break down the problem into like several levels and solve them step by step. Also, we face a challenge of how to synthesize the QMO sentry gates at the logical circuit level and how to transform the fermion boson mixtures operators to CV-DV basis gate sets. Then we need to consider the multi-qubit polystring synthesis in our hybrid CV-DV setting, which is quite unique to the qubit-based architecture. And we first proposed a new schema inspired by the phase kickback proposed by Liu and etc. And use Q mode as a carrier of the qubit entanglement information. Finally, we also face the challenge of limited connectivity of the hardware as which it requires us to just offer hybrid CV-DV circuit level mapping and routing support. So we will show how to solve these challenges by these approaches shown in this PowerPoint. So let's look at the Hamiltonian model. It's a part of Harbor hosting model, a very famous model. And so it's represented in a mathematical format. So the Hamiltonian edge is a mixture of fermionic operators and bosonic operators consisting of products of like fermionic creation operator, C dagger, right? And annihilation operator, C, with a fermionic spin index named as sigma, ranging from 0 to 1. And the qubit index, the axon, named as I and J. It also consists of products of bosonic creation operator and B dagger and annihilation operator B, and product of fermionic number operators with bosonic operators. So let's now look at the corresponding example Hamiltonian grammar representation. So we can see that the tensor, the sum over and tensor prod actually denote the sum over symbol and tensor product between the fermionic number operators and the bosonic creation operator and bosonic annihilation operator. So this is like a whole process. The pipeline, yeah. So starting from the Hamiltonian formula in mathematical form, we will like further translate it into a DSL-based, as mentioned above previously, like Hamiltonian grammar representation. Then we will convert the DSL into an IR consisting of polystrings, right? The polystring over there, and the operator expressions, including the bosonic and the hybrid. Moreover, we'll match the fermionic and bosonic operator terms and synthesize them into logical CV-DV circuits in CV-DV QASM format, a format that we propose and is very similar to Open QASM syntax. And finally, we map the logical circuit and polyterms to hardware-compliant physical circuits and output the final CVDVQASM program. So in the transition process from the IR to the logical CVDVQASM for sequences that involve first or second order Hermitian polynomials of annihilation operator and creation operators. We initially just attempt to map them to the fundamental gates in this table, and using pattern matching. And if the operators, they match specific gate patterns and with appropriate, let's say like parameterization, the corresponding basic gates are applied directly. So even though some operators, right, can be directly pattern matched, but most Hamiltonians actually consist of polynomials of Fermionic, Bosonic, creation operator, and annihilation operators, and cannot be directly implemented on quantum hardware circuit, and must be further decomposed and approximated. So to achieve this, we have the quantum algorithms, so which are not just like very abstract mathematical formula. They kind of like encode a way to that the compiler must follow to transform the physical models into executable quantum circuits. And here we provide two fundamental rules, trotterization and BCH. So trotterization is a way of approximating the sum of operators on an exponential, and BCH is a way of approximating the commutator and anti-commutator on the exponential. So with these fundamental two rules, we can use a formula anti-commutator AB plus commutator AB over 2 is equal to AB to simulate the product on exponential. So in hybrid CVDV architectures, many operators involve both a qubit and a Q mode. So such as like hybrid controlled displacement gate or qubit oscillator couplings. And to compile this, we can also employ the block encoding, which is a very powerful technique to embed non-structural operator or non-structure operator and into larger unitary. And besides this, there are also different ways to approximate the product or sum on the exponential with different gate sets or codes and conditions in our next slide. So together, the elements introduced in the previous slide establish the foundation for the template rewriting-based approach proposed in this paper. As summarized in the table, we define a set of synthesis and decomposition rules, including basic sum and product rules that enable recursive breakdown of a Hamiltonian into simpler components, and by reformulating the decomposition task as a template matching compilation process, our method iteratively applies its rules to sequences of annihilation and creation operators. So this recursive process continues until the resulting terms align with all basis gates in templates in the hybrid CVDV gate set, and allowing for scalable and automated Hamiltonian simulation. So let's look at the current nonlinear term for example. So e to the power of a dagger square and a square. The overall rule-based recursive template matching process is a DFS process. So we may reach a dead end, and we will set a time threshold if it reaches all dead end, and where it can meet any rules operator template or condition to get further decomposed. Now, let's look at a successful path highlighted in green as an example, and we can split the exponential into a dagger square m and a square n, and we can find that it matches rule 11 since its condition mn is equal to mn dagger, and together with BCH, we can find that it can be further split into a dagger square into like a dagger and a dagger, and it matches rule 6 condition, and the operator is operator template. It's like this, so forth and so on until repeat this process until it produces only basis gates in the CVDV gate sets. So since there exists many multi-qubit poly operators on exponential in our Hamiltonian, and qubits are not directly connected with each other, especially say like in a superconducting scenario, and we propose a schema to synthesize arbitrary multi-qubit polystrings on hybrid CVDV platforms. And this approach is inspired by the concept of phase kickback in DV systems, where the phase of a control qubit is affected by operations on the target qubits, and the detailed implementation is shown in the U here, U equation here, and P1, P2, Pn represent the detailed multi-qubit polystring, P1 tensor product P2 to Pn, and dk is a displacement gate of case Q mode, and the CDK P1N are controlled displacement of alpha. So in our method, Q modes act as an entanglement medium to transfer the quantum entanglement among qubits through a sequence of conditional displacement gates. For instance, the qubit control Q mode displacement and the conditional displacement gates, such as that the desired operations in the qubits are achieved, but the effects on Q mode, they are cancelled. And the U implementation relies on the, like mentioned previously, on the multi-qubit control displacement gate proposed by Liu, etc., consisting of a displacement gate and control parity gates conjugated by Clifford gate. Now let's look at the demo here, and see the Q mode highlighted in blue interacts with every qubit on the path from A to N, and while control parity gates, and it performs an unconditional displacement gate and then travels back to A's location while performing the CP gates. So CP gates here denote the control parity gate, and this implements the CD gate mentioned above. So as mentioned above, as mentioned previously, so we mainly focus on superconducting scenarios, and the qubits Q modes are connected as shown in the picture. Right, so there exists 3 kinds of interactions: Q mode, and Q mode, qubit, and qubit. So since Q mode interactions are only limited to the adjacent Q modes, and qubit interactions are only limited with Q modes associated qubit, a Q mode swap gate is required for mapping, which consists of 1 beam splitter gate and 2 phase space rotation gate, with the latter having a very low latency in comparison with the former. And for qubit interaction, we were using ancilla Q mode to move between qubits to mediate the interactions and complete gate operations mentioned in the previous slide. So the working frontier in Genesis is an internal marker for each qubit Q mode that tracks how far a scheduling has proceeded in time, enabling the compiler to insert a line and route gates correctly while respecting the gate dependencies and hardware constraints. And here we will use a Quiski Saber-like reward function to execute the gate from the frontier and update it. And for qubit mapping, we need the ancilla Q mode as the messenger to traverse all relevant Q modes. And the traversal paths, which can be further routed and optimized, can be reformulated as this relaxed Hamiltonian path problem. Similar to a modified traveling salesman problem, and unlike the closed path TSB, this allows revisiting the vertices and does not require returning to the starting vertex. And we can take a look at an example here. So we want to traverse the node, say the Q mode, like A, B, C, D. We can pick any Q mode as a starter, and the optimized order DCAB actually excels 1 beam splitter gate in comparison with alphabetical order AB, ACD. So while native swap gates exist only for Q modes, qubit movement can still be considered in CVDV architecture thanks to the Yuan, etc. Similar gates can enable indirect qubit-qubit interactions via ancillary Q modes, effectively simulating a qubit swap using 3 CNOTs. However, this requires 12 control displacement gate and 12 Q-mode swap gates, which is very expensive, making it about like 24 times more costly than simple beam splitter gate. And this method is only practical when frequently interacting qubits are physically distant. And if that applies, we just initiate a clustering step to bring qubits into closer connectivity. And this design, which we call floating qubit, provides greater flexibility for long-range interactions. And we have implemented 3 kinds of ways to solve the optimized ancillary Q-mode routing problem. Like structural accepting algorithm is generally the best, while dynamic qubit floating performs the best in some cases. And so here is our implementation in recap. And we have open sourced our code in GitHub. You can scan the QR code here. And we have evaluated the compilation on multi-qubit polystring on 20-qubit Hamiltonian, such as the RH and BH2, with polystring ranging from 631 and 1884. We also use JW and BK encoding to transform the fermionic operators into polystrings, which later just turns out that the JW consistently outperformed the BK. And we have also evaluated the general Hamiltonian simulation compilation on 6 Hamiltonian models, such as hyperhosting model, both hybrid model with at most 60 qubits and 120 Q modes. And in the future, we may intend to support more architectures like a neutral atom and include better relocate strategy when compiling multi polystrings. Also, we can flexibly include and adopt more rules in the recursive decomposition stage with more error analysis and unitary verification and improve our compilation efficiency and robustness. So yeah, thanks. Sorry for the exceeding time.
Okay. Thank you very much.